hear me? Good afternoon. Welcome to today's class. We're mostly going to spend time covering the links layer today. We got done with the portion, with the material I wanted to cover in the network layer control plane as of last class, where we looked at the main routing. We didn't quite look at one part, which is the STM control plane that I said is DIY or self-reading. We're just going to skip network management. You're welcome to do it on your own, but your syllabus really ends here because we want to move on to please the link there. Okay. I was a little rushed at the end of the last class, finishing into domain routing. So this is a good time to do some quicker questions to make sure that we stay. So that's the first question. Code A individual. Let's do 25 seconds for this. Let's now keep it open. Alright, everybody can get done. Router may learn about more than one router destination. Sorry, this question doesn't even parse right for me. What did I do? Router may learn about more than one router. Oh yeah, that's not a question. Sorry. No wonder I'm getting confused. Alright. Sorry. Good. I forgot my coffee after lunch. That's why. Alright, that's your first question. Which of the following protocols is an inter-domain routing protocol? Let's stop it at 1:15 or do a countdown. 5, 4, 3, 2, 1. So the answer is indeed D. That is there is only one inter-domain routing protocol in the internet, right? So you don't have to think about it. ISIS is a Cisco proprietary link state routing protocol, like OSPF, but it's not open, right? Okay, that's the right answer. Which of the following is not a function of an inter-domain routing protocol? I didn't give you a time, so we'll wait till 75 is over. 5, 4, 3, 2, 1. Popular choice is choice D, and popular choices are good in this class. Computing the shortest path. First, there's two giveaways. The first giveaway is it's within the same AS. Okay, that's not quite enough because intra-domain considerations are also part of BGP's route selection to a remote destination. You select a route to a remote destination based both on the AS level path as well as how to get out of your own network quickly. So there's intra-domain considerations. However, computing the shortest path should be a dead giveaway because BGP's first criteria is policy, not shortest path, right? So computing the shortest path to a border router within the same AS, it is very much the essential, part of the essential goal of an intra-domain routing protocol, and therefore that's not inter-domain, right? Okay. Which of the following is not true? Right, 5, 4, 3, 2, 1. That's good. Export determines what you export or re-advertise, right? You import a route, adopt a route. You receive a route, and the import policy determines amongst the received routes which route is adopted. And then the export policy determines whether the imported route is re-advertised to one or more of your neighbors. Right? So that's the others are just truths. You can verify that. That's the right answer. Oh, why is that not green? Sorry, I double clicked it. I think this is the last question. The following is not valley free. So provider.
Like these things are done.
So A looks like this. B looks like provider tier test. Which of the following is not valley free? Alright, let me first close this. C is provider customer. D is customer peer. So that's customer peer. That's your problem right there. Okay? Peer customer, let's verify E as well. E is peer customer. Okay? What's the regular expression I gave you? Any number of customer to provider links, including 0, followed by exactly one peer, or exactly 0 or 1 horizontal peer link, followed by 0 or more provider to customer or downward links. That's valley-free routing. Okay? So if you want to think of valleys, this is a valley. Okay? That's why it's called valley-free routing. It's not just a random terminology. This is all hill, right? This is more of a plateau. There's no valley or anything here. But here's the valley, okay? But really, that's the expression to keep in mind. That's the ultimate check. Yes, question?
Is there a light above that black forest for there?
Yeah, so I tried. Does anyone know where this light is?
Maybe right there.
Does that help?
Yeah, there's if you want to pedal that, but
Maybe that's that side. There's one like that. I think the middle one's just gone coupled too, because there's only one switch and it turned on these two.
that's fine. The other two do better, so.
Yeah. All right. So therefore, what's our answer? That's D. And so that's the right answer. Okay? Not the popular answer this time. Dollars are flowing from customer to provider. So dollars flowing this way. Dollars are also flowing this way. Okay? Generally not money is either not exchanged in peer-to-peer links because it's a relationship of more or less equals. Sometimes it may be. We just really don't know what these pricing policies are. Okay? Questions? So economics is what fundamentally drives interdomain routing policies. What route you adopt, what route you advertise to somebody else, right? Here's another example of a route. Oops. What about this? Is this valley free? 0 or 1, right? There's nothing of this kind, nothing of that kind. But there can at most be 1, but there's 2 horizontally. So why is this not allowed in the real world? Like, what's the economics of it? Money, where's the money? What's the money saying? Well, the money is saying that this, let's call this A is A, let's call this A is B, let's call this C. B is carrying packets from A's customers over to C's customers. It's not getting any money here, it's not getting any money here, but it's doing work. This could be a large ISP, it's carrying it from this end of itself to this end of itself, doing work for these two. Because their customers are benefiting, but it's not getting any money, it's doing work for free, okay? You cannot make the same argument here. Why? Because this AS is benefiting its customers. It's doing work here to take packets from here and sending them to its customers, but it has a customer obligation here to do that work for its customers. It's not getting any money here, it's getting some money here. So money drives these economic policies, and that's the reason interdomain routing policies commonly don't satisfy the triangle inequality, which is sum of two sides is always greater than the third side. In the internet, you can go from one place to another and go from the other. Ping delays going from one place to another place to a destination. And that might actually be shorter than a direct route, because these direct routes that you're getting from your ISPs are not necessarily shortest, okay? By ping delays or really any metric. You're first optimizing revenue for the ISPs along the way, okay? And this is not an uncommon case. About something like 40–50% of internet routes are known to have detour routes. And you could get a better latency by going somewhere else and then going to your final destination. So it's not a common case at all. I'm sorry, it's not a rare case. Triangle inequality violations are a fairly common case. And the reason for that is economics. Okay, before we move on, any questions about routing, interdomain or otherwise? Alrighty. So this is the last of the chapters we're going to see. I usually try to cover at least a little bit of wireless networking, but unfortunately we're running a little behind, possibly because of the class of the size and more time on clicker questions and whatnot. Right? I don't know. But the link layer is an important part of the network protocol, the 5-layer network protocol stack. We've seen 3 layers so far: application, transport, network. Fairly complex thing, but the network layer is very rich. It goes from a subnet of internet to another subnet of internet across intra and interdomain routing protocols, right? So we've seen a very, very fascinating level of richness of protocol design, algorithms, and so on. You might naturally wonder, well, what is the big deal about sending packets from one end of a link to another end of a link? That is what the link layer is about, right? This could be a piece, this could be a wire, like the Ethernet cable, or it could be a wireless link, in which case it's sort of, from A's perspective, it's more like a range of its radio transmission, right? Everybody in this range is connected essentially to A with a wireless link. So that's the main difference between wired and wireless. Most of the principles we study about the wired link layer for the next remaining 3 classes, most of them will apply also to wireless, okay? So that's the problem. One end of a link, packets to another end of the link. In this problem, you have some of the usual suspects that we've seen. So one is error detection, possibly correction, although Ethernet only does error detection, not correction. This is similar to what transport protocols do. Whatever problems you're solving in a transport protocol from one endpoint of the internet to another endpoint of the internet across a multi-hop internet path, most of those problems to some extent also appear at the link layer. So error detection correction is one example. sharing a broadcast medium, this is really not something that we saw in a transport protocol. But in both Ethernet and Wi-Fi, the medium is shared. When one node speaks, all the nodes connected to that medium can hear. This results in a very important problem we solved called the multiple access problem that we will see today. So it's not always two nodes, right? That's the thing to keep in mind. It's as if there's a T connector here, and there's a C, and there's a D here, there's an E here. In wireless, it's implicit, right? But even in wired networks, the link layer fundamentally, inherently, is a broadcast medium. It's not a point-to-point medium. This is why you can sniff packets on Wireshark, on Ethernet, or on Wi-Fi, right? You can hear what's being sent, even though it may not be destined to you. It's your lower layer, it's your link layer really, that decides whether the packet's actually destined to you and is to be sent up the higher layers of the protocol stack. Link layer addressing, it's different from IP addressing. You're all probably familiar with MAC addresses. We'll see why we have two addresses. Why do we fundamentally need two addresses in design and architecture? Then we'll look in somewhat more depth at Ethernet, at how to implement some of these conceptual ideas. We'll go about it the same way. We'll first understand principles, the abstract problem, and then look at how Ethernet implements it, how data center networks are designed, combining actually link layer and the previous network layer concepts. Okay. So we'll start with, sorry, I'm going to just skip over some of this stuff. This is a good analogy slide. We've seen analogies, right? Transportation analogies in every chapter, transport layer, network layer, and so on. So if you think in terms of transportation analogy, and think of a tourist like a datagram, then a transport segment is like a communication link. Transportation modes are like link layer protocol. You take an Uber from here to the airport, and then the next link is an air link, and then after you get off there, you take maybe a subway, that's another link. Those individual links, those individual transportation modes, those are the equivalent to link layer, right? And of course, your routing algorithm is the trip plan, that's the control, that's like your travel agent, right? Datagrams can get dropped. I guess it doesn't make quite an analogy to imagine a tourist really getting dropped anywhere along the way, but you could say miss a flight or miss a ride or something. Okay. Fundamentally, the problem that makes going from one end of a link to another end of a link hard is this problem of multiple access. Okay? To some extent, this is true in the real world too. You want to get an Uber, a ride, everybody's using the phone, there's competition during peak times, prices are high, your wait times are high. Okay? So that also sort of gives you a sense of why the link layer still has a great richness of functionality as well as algorithmic complexity in how it goes about solving that problem. Okay, so if you think in terms of functions, generally for the link layer, not specifically Ethernet or Wi-Fi, then framing and encapsulation, this is one part of the functionality. For the link layer header, every header at every layer has a source component and a destination component. The link layer is source MAC address, destination MAC address, among other things, right? Question of reliable delivery. Does the link layer provide reliable delivery from one end of a link to another? Well, we've seen before that this is not strictly a necessity. And internet thought in general is many links, right? TCP needs to do reliability in an end-to-end manner, no matter what. No matter how much you engineer one link, reliability has to be done end-to-end. However, some link layer protocols may actually give you a reliable link to keep trying from one link to another until you accomplish the job 100% here, and 100% here, and 100% here, and so on. Ethernet, Wi-Fi don't give you that kind of reliability. Common link layer protocols don't, but there are link layer protocols that might. Okay. So we generally try to avoid redundant functionality. This is also something that we've seen as called the end-to-end principle, which is don't put redundant functionality at lower level. If you anywhere for correctness, need to do it at the higher levels of the stack. Design this somewhat loosely or carelessly, because there's diminishing value to over-engineering every link. So that's why we don't spend too much effort making links reliable. Some link layer protocols have flow control. Flow controllers don't overwhelm the receiver, right? Pretty much any link layer protocol will have error detection. Some, not Ethernet, not Wi-Fi, might also have error correction. Okay, we'll actually look at one very simple example of how to correct errors. And link layer protocols, like transport layer protocols, can be either half duplex or full duplex, bidirectional or unidirectional. Okay, TCP is bidirectional. Link layer protocols, really, it depends on the link layer protocols, what kind of communication semantics they offer. Okay, so where is the link layer implemented, right? It is part of every single host. Just like the network layer is part of every single component along the way, or well, practically every single end host, every single router, switches. The link layer is actually part of switches, part of routers, part of networks. It's there, processing for pretty much any design, right? Any node along the route. The link layer logic generally resides in what's called a NIC, or a network interface card, right? So my computer, my laptop here doesn't really have an Ethernet port, but it has like a few USB-C ports, so I need an adapter to plug this into Ethernet. Wi-Fi is sort of in the, right? This is just the more recent Macs have just started issuing Ethernet ports just in place of USB-C. So I'm going to pass this around. This is a toy I got. You can look at it, pass it around. You've probably seen one of these. This is an example of a NIC with an Ethernet port that's dangling at the end of it. It's what could typically go into a laptop, right? So that logic, that's on that board, on that little board out there. That looks like the one shown in this picture. Link layer protocols are implemented in a combination of hardware, software, and firmware. Firmware being a term sort of for something in between the two, something that can only be updated by the original manufacturer. So let's look at how these datagrams are propagating across the 5 layers of the protocol stack, specifically zooming into the link layer. This shows you a datagram that is being sent from the network layer, until which we understand how transport sends encapsulated to an IP datagram, and then sends it downward to the link layer. At this point, the link layer is going to take that IP datagram, source IP, destination IP, the rest of the IP header fields, encapsulate that in a link layer header, which has a source MAC address and a destination MAC address on the sending side. It'll also add some error detection information. Okay. In the case of reliability of providing link layers, it may add additional information for reliability as well. When it gets to the other side is going to look first for errors. If the checksums don't match, it's going to drop this packet, this frame, just another name for packet at the link layer. And if all the checks pass, then it is going to send it over to the higher layer, which on the internet will be IP, network layer, right? And then it goes through transport. We've seen how all that works before. So that's your basic model, and that functionality largely resides as driver code for that NIC that's being passed around. That's just software. Some of it is just built into the hardware itself, and some of it is just in between, right? All right, so we're going to start with error detection and correction. You haven't yet seen an error correction protocol, but we'll see a glimpse of a very simple error correction protocol. We are familiar with the error detection problem. You have a bit error prone link. You have some datagram that is to be sent. We're going to denote as EDC the error detection and correction bits. Some amount of redundancy is being added. Some amount of additional bits are being added to the packet so that when it gets to the other side can do some checks for errors. We add in the checksum. EDC is just means the checksum, right? When this packet gets to the other side, we know what the rules of engagement, the rules of the game are here. If the check happens, if all the bits in this received D prime, or D prime, EDC prime, if all the bits are okay, that means the checksum of D prime turns out to be EDC prime. Or if it's not okay first, we for sure know there's an error, right? However, we also know that if the checks pass, that means it's just that layer that has decided that there's probably no problem with the packet. There might still be errors that are undetected in the packet, okay? So error detection schemes generally have some false negatives, which means they can miss some errors. But if they say there is an error, there's definitely an error, and you discard the frame errors. Okay? So let's look at a very simple example of how to correct for errors, not just detect errors. We're all experts in detecting errors. You're implementing that as part of project 2 or have as part of project 2A already, right? Most of you. How would you correct bit errors in the packet? Let's say you have an array of bits, the same, or bytes, or whatever, right? What might you add in the datagram so that the receiver is able to not only detect if there's a problem, but also fix some problems in the packet? You can be as inefficient as you like. Anurag?
Oh, I can add a parity bit, or like I can take the bit and every 2 bits is essentially a single bit, so that I know if one of the alternate, like every adjacent bit, not every adjacent, every 2 bits is a single bit, so that it's double redundant. So that like 2 ones are just a 1, and I will know that if there is an error, I will know.
Well, you're on the right track. I'm not sure if the rest of the class is necessarily with following you. Where did you encounter this, may I ask? We just happen to know of it somehow. Okay, so what Anurag is describing is very close to a system I'm going to show you in a second, but I first want us to think intuitively, right? Let's say this is your datagram. The size doesn't really matter, but let's say this is a 16-byte datagram, right? Small datagram. You want to pad this with some checksum type information so that when this goes to the other side can not only detect if there's a problem, but if there are small problems, it can also automatically correct it, right? So here's a very, very inefficient, but dead simple, trivial scheme that we do. I am just going to send 3 copies back to back of the same packet. Okay? So I'm going to send 48 bytes instead of the 16 bytes and leave the same. I told you it's very inefficient. And then I'm going to just, if all 3 are the same, then there's no error. That's my protocol. If one of them doesn't match, but other 2 match, I'm going to take the majority and pick that as the correct one. And I'm going to assume that this one got corrupted. Right? So I added triple redundancy, which is a huge amount of overhead. I'm still not guaranteed to be able to correct all kinds of errors, but if somebody told me exactly 1 byte is going to get corrupted, which will be the case in project 2, because project 2 corrupts exactly 1 byte in any 100 byte range, so 16 is less. If I told you exactly 1 byte for me, nothing or up to 1 byte could get corrupted, then this is a perfect scheme, right? If a byte got corrupted here, you know that these 2 will match exactly. You not only know what the corrected data, you know what the corrected data is, you know exactly which byte got corrupted. This is a very high amount of overhead, 3x overhead for tolerating 1 byte error, right? We can do better than this. We can do much better than this, asymptotically better than this, using parity bits, like Anurag was describing. What's a parity bit? A parity bit is just the 1-bit sum. So it's just the sum of all the bits mod anything mod 2 can only be 0 or 1, right? That's what a parity bit is. You can also think of it as simply an XOR of bits. 1 XOR 1 is 0, 0 XOR 1 or 1 XOR 0 is just 1, 0 XOR 0 is still 0. Okay? So in this case, the parity bit happens to be 1. You can also think of this as simply counting the number of ones. That's also cool. If there's an odd number of ones, parity bit is 1. Even number of ones, parity bit is 0. Okay, so far we've added only a parity bit. How does this help us correct errors? Well, we're going to add quite a few parity bits, but still not as much of an overhead as this example gives you. Okay? It is going to be a non-trivial amount of overhead no matter how you try to do it. Correction is expensive. Much more expensive than detection. Remember that in detection, you could just add one more byte, a 17th byte of checksum, and be done with it, right? But for correction, we're going to add two-dimensional parity of this way, where for every row you have a corresponding parity bit, and for every column you have this is the parity bit for this column, this is the parity bit for this column, this is the parity bit for, or this is the parity bit for the last row, and so on. So you take the bits, like in this example, let's say these were 16 bits instead of 16 bytes. You would put them in a 4x4 matrix. That's your 16 bits. So that's your data. And then you compute 4 plus 4, 8, or 2n, or 2 times square root n bits of parity. This scheme was 3 times n. 2 times square root n is much better than 3 times n. Okay? It's not constant. It is expensive. All right, what did we get by doing it? How are we going to not only detect but also correct an error? So here's an example. In this example, when the receiver gets the packet and checks that all the row parities match. There's 3 ones, so this parity is 1. There's 4 ones, so parity is 0. 3 ones, parity is 1. You can check that all of them match. Okay? If somebody told you that at most 1 bit could get corrupted, no more than 1 bit could get corrupted, right? That is an assumption. That may not be true. But if somebody promised you or guaranteed to you that no more than 1 bit can get corrupted, then you can use these parity bits to not only know that some bit has been corrupted, but also know which bit exactly was the one that got corrupted and flipped. Good. Okay, so the question to ask is, if any parities don't match, which is the bit that you need to flip from 0 here to its original value 1, so that if you did that, all the parities then will make sense.
Is that diagram supposed to show ridiculous no errors?
Yes. The left.
That most column has 2 ones.
Interesting. That is a mistake. This is slides from the textbook. Yeah, so thanks for pointing that out. That is a mistake, right? But you can fix that and let the rest will still match. Okay. So this needs to be a 1 plus 1 0. And if you get a packet like this, we see that there's 3 ones here, but the checksum is 0, and there is exactly 1 1 here, and the checksum is 0. So the intersection of that row and that column, if you flip the bit, all the checksums will match, ignoring the fact that this 1 is just a mistake on the slides. Okay, sorry about that. That's an example of how we're using parity bits at a non-trivial cost. Okay, square root n asymptotically, but it's much better than doing something like linear redundancy. Common link layer protocols like Ethernet or Wi-Fi don't try to correct errors; they detect errors. Right? I'll skip over this little just so you get the part that you've seen. They use instead a different type of checksum for error detection. This is what Ethernet uses. This is also what Wi-Fi uses. And this checksum is called a cyclic redundancy checksum. Okay? cyclic redundancy checksum doing? Well, what is it good for? Why do we have a different checksum? When I first introduced checksums, remember one of you, I forget who, had a class question asking, is there something you assume of the nature of bit errors that occur in a packet? And I said, yeah, well, bit errors at TCP and UDP level, we don't assume anything, we just assume bits can randomly get corrupted. But at lower levels, like the link layer, you typically, on the wire at least, errors typically happen in bursts. It's not that bits are randomly getting flipped on the wire. That usually doesn't happen. Usually what happens is a contiguous string of bits gets corrupted, right? We want to protect against, we want a checksum that's particularly effective at detecting these kinds of burst errors as opposed to random errors. We've already seen that TCP UDP style checksums, they're not very robust. You can easily flip 2 bits and ensure that the checksum still remains the ones complement sum of 2 byte words in the packet. That's TCP UDP checksum, that still remains the same. For detecting burst errors, we use a different kind of checksum called cyclic redundancy checksum, where you have a data that's called D, and you have a checksum that's of length R plus 1 bits. And you have a constant, this is part of the protocol, if you will, that's called a generator that we know is G. So all I've told you so far is there's R plus 1 bits of the generator as well as the checksum that we're going to compute for data T. What is this R? Why do we have an R plus 1 bits? Well, the nature of this R is such that it'll tolerate any bit errors up to R bits. We will pad the original data using this cyclic redundancy checksum as follows. We'll take this data D. Think of this data D as a big number, right? It's just a big number in bit. We will bit shift it, we'll left shift it by R bits, which is equivalent to multiplying it by 2 to the R, right? Multiplication by 2 to the R is equivalent to left shifting by 2 to the R. We're now going to do some funny math here. Our math is going to be XOR arithmetic. In XOR arithmetic, both addition and subtraction are XORs. So 1 plus 1 is 0. 0 plus 1 or 0 XOR 1 is 1. 1 XOR 0 is 1. 0 XOR 0 is 0. 1 minus 1, subtraction in XOR arithmetic, there's no such thing. It's just plus, minus, everything is just one operation called XOR. In that arithmetic, we can think of this checksum R, that is R bits long, that's generated using a generator that's R plus 1 bits long, as the remainder when this whole thing is divided by G. So here's the way to think about it. We choose the R CRC bits, so these bits, such that that whole number, D times 2 to the R, plus the checksum capital R, which is this whole generator thing, is exactly divisible by G. That is how we are generating the R CRC bit. So we're asking the question of what R bits should I put here such that this whole thing is exactly divisible by G, which is an R plus 1 bit number that's just baked into the protocol. It's just some constant. Okay? The proof of why this can tolerate all burst errors less than R or up to R bits or less than R plus 1 bits, not too complicated, but that's something that I'm not going to go into in this class. But how to compute this is fairly easy. Okay? It is literally primary grade easy, like long division. If I asked you what number I should add to 63 in order to make it divisible by 5, you can tell me in a fraction of a second that you need to add 2. right? Or what's the smallest number I can add to 63 to make it divisible by 5? You can tell me it's 2. 65. That's what we're doing, except we're doing this in XOR arithmetic. So here's how the arithmetic proceeds. We want D and R attached at the end, which is a number that is D times 2DR, the left shift, plus this capital R. Plus is the same as XOR. Okay? We want that to be some perfect multiple, some integer n times G, which is just a constant that's output when it gets long. So how do we do this? How did you answer the question of what do I need to add to 63? What's the smallest number I need to add to 63 in order to make it divisible by 5? What you did was, one way you could do it is divide 63 by 5 and notice that the remainder is 2. And yeah, then what you need to add is the generator, in this case 5, minus whatever is the remainder. In XOR, minus and plus is all the same. And the division occurs as follows, right? So if you want the first property, D times 2DR XOR G, I'm sorry, XOR R is equal to N times G, we can multiply both sides, or we can XOR both sides by R, and you'll get this equality. Anything XORed by itself just takes it away. Okay, so on the left we're left with D times 2DR, on the right we're left with NG XOR R. Okay. Equivalently, if we divide D times 2DR by G, we want the remainder R to satisfy this property. R should be the remainder when we divide D times 2DR by G. In XOR, this is like saying, in the 63 and 5 case, this is like saying, divide 63 by 5 and whatever is the remainder, that is what you need to add. It doesn't quite work in the 63 and 5 case because it's traditional arithmetic with pluses and minuses, but in XOR world, that is exactly what this means. You take the remainder of D times 2DR when divided by G, and that exactly is what you need to add to D times 2DR to make the whole thing divisible by G. Alright, so let's look at a very concrete example so it's very clear how we're doing this arithmetic. Let's say this is your generator G, 1001. It's an R plus 1 bit pattern, 4-bit pattern, which means it's designed to tolerate all bit errors of length 3. It can tolerate bit errors, not bit errors, burst bit errors of up to length 3. So 1 bit error, 2 continuous bits, or 3 continuous bits. It's guaranteed to detect them accurately. Let's say that is your 1, 2, 3, 4, 5, 6 bit data. In order to do our computation of D times 2DR to the G, I just multiplied our data with D times 2 to the 3, which is left shifting by 3, right? So this is what the original data looks like. This is the left shifted by 3 bits, which is the same thing as multiplying by 8 to the 3. We're just going to do division now. Okay, this is like, I don't know, 5th grade, 4th grade, whatever. That's the first step. Sorry, let's go back. That's step 1, right? 1001 times 1001 times 1 is just itself. Notice what we're doing here. Addition, what we would normally do here is subtraction, right? When you're doing long division. Subtraction and addition are the same. 1 XOR 1 is 0, 1 XOR 0 is 1. At this point, this is of course not enough to be divisible by this, so you pull over the next number here, which is exactly what we do in long division. And you see this is 101, that's still not quite enough, so we're going to put a 0 up there and pull one more number, which making it 1010. At this point, we have enough bits, and so we can now put one more of these. Next step is the division like before, so subtraction, which is the same as addition. 0 XOR 1 is 1, 1 XOR 0 is 1, you get 1, 1. Pull down the next 0, that's not enough, so you're going to pull one more 0, at that point you have 4 bits. You keep doing this, that's the remainder at the end. Okay, so in the XOR world where addition and subtraction are both XOR operations, compute executing this remainder corresponds simply to this long division that we did here. And you can now check that, sorry, if you take these bits 0, 1, 1 and put them here, so this was originally the 1, 0, 1, 1, 1, 0. And in these three bits, you put 0, 1, 1. You can flip any contiguous set of bits of length up to 3 and verify that on the receiver side the error will be detected perfectly. 4-bit errors cannot be detected perfectly. They may the checksum may still pass. Just like in UDP TCP, the checksum could pass, but the packets could still be corrupted. That can happen with 4-bit or more errors that are burst errors. It can also happen with 2 or 3-bit errors that are not burst errors. So if 3 bits got corrupted that are not contiguous, this is not guaranteed to protect against that either. Or this is not guaranteed to perfectly detect that either. But burst errors of up to 3 bits, this checksum will detect in this bit pattern. Okay, and that's what it is. The remainder you get when you divide the data left shifted by R bits by just a constant. That's a protocol constant. That's cheap. That's called the generator. Questions? This is the checksum that's used in both Ethernet and Wi-Fi. Very, very popular link layer protocols that we all use. Every single frame or every single IP packet, internet packet that you're sending on most links is going over Ethernet links, right? Or Wi-Fi the first hop. Every step on every link, CRCs are being computed using this checksum algorithm. Right? So keep in mind that burst errors of your R bits, if there's a burst error longer, or if it's not a burst error, possibly shorter than R bits, are not guaranteed. Let's move on to the multiple access. Do I see anything? No. Okay, multiple access problem. This is the central algorithmic challenge, right? At the link layer. I told you that the link layer is inherently a broadcast medium, right? Links can be point to point if there is exactly 2 nodes connected to 2 ends of Ethernet. But in general, an Ethernet switch or a hub, which is a more primitive device, can have more than 2 nodes connected to it. Or if we have things like T connectors, then all of these are part of the same Ethernet, which means if any node speaks, everybody can hear. So it's sort of like a party going on. And our challenge is that we want to ensure that anytime exactly one person speaks, one node speaks. If more than one node speaks, then nobody hears anything. That's the game, that's the challenge. Okay? And it's the same medium that they have to coordinate, right? So this is the multiple access problem. A single shared broadcast channel. 2 or more simultaneous transmission by nodes means interference or collisions. Right now, I'm the only node in this shared broadcast medium, which is the air around us, that's talking. You can hear me hopefully fairly clear. But if multiple of us were going to be talking all at the same time, then, well, the human ear is actually very, very good in parsing out some signals. And we'll see at least one example of a link layer protocol that works with that in Fusion. But you would agree that it would be hard to understand who's saying what if multiple people start talking simultaneously. So we need a distributed algorithm that determines how nodes are going to share the channel. Who decides when I talk, when Thomas talks, or when Joe talks, when GC talks, when Carlos talks, or what? Who decides this? We need a distributed protocol because there's a central node that decides it, and it's not fault tolerant enough. So we would ideally like this to be distributed. And the catch, the big catch is we need to make this decision of who is going to talk at any point in time using the same medium. So in the process of talking to decide who is going to talk, you can again have collisions. That's what makes this challenge. In this classroom, we don't have that problem, right? If somebody wanted to talk, they were just going to raise their hand. And so I'm going to just let them speak. So there's generally no collisions. If I see that somebody wants to say something, I can see it. That's an example of an out-of-band channel. We have two channels. One is the auditory channel, and one is the optical, the visual channel. With a secondary out-of-band channel, this problem becomes very trivial. If you want to control the auditory channel, you just raise your hand, you use the visual one, and I give you control. Problem is trivial. But now imagine the problem scenario where all of us, every single one of us, let's say we're all senators, right? We're all blind senators. And we all care intensely, passionately about politics of our country. And we love to argue about it like senators do. But we can't see each other. We're all blind. We can only hear each other. So that limits us to no out-of-band channels, no visual channels. We're all in the same room, so we don't hear each other. And we need to decide who gets to talk. And we need to do this with some ground rules of the Senate, the blind Senate. We have some R bit per second channel, which think of it as, we all can process, I don't know, 10 words, or at most 4 words per second, or something like that, right? Whatever is the human number of words per second that we can process. That's our R bits per second. The first rule says when exactly one node wants to transmit, it should be able to speak 4 words per second, the full capacity of the channel. So if I'm the only person who wants to speak, I don't know if you want to talk right now, then I should be able to speak at the bandwidth of 4 words per second. We should make progress in the Senate. The second one is when multiple nodes want to transmit. This is like the no filibuster rule, right? What's a filibuster? Yeah?
You talk and make sure nothing happens.
Yeah.
Congress.
Yeah, so it's a waste. It's just wasting time. It's baked into our constitution or one of the amendments, and it's exploited. So this rule says, this is essentially from a resource management perspective, the rule is simply saying that there should be fairness of resource allocation. If I, Joe, and Carlos, all three have some burning opinions to share, then I shouldn't hog the channel the whole time. I should hog the channel about 1/3 of the time, because it's 3 people within 10 minutes. Okay? And the latter two are more like high-level design property. It should be fully distributed. So we don't have a vice president who's the head of the Senate, who has a gavel and decides who gets to speak. There's no such thing. Okay, we are decentralized. Decentralized protocols are better because they don't have a single point of failure, right? If the vice president calls in sick someday, then the Senate should still be able to make progress. And of course, simplicity. It's a hard to quantify property of the protocol. The simpler the protocol, the easier it's to implement, the easier it's to diagnose, debug problems, maintain, whatnot. Okay, so that's the problem statement. How do we solve this? How do we decide exactly one person speaks, but as much of word throughput happens when lots of random people in the room want to all speak at the same time and we're all blind? So the problem makes sense. It's a problem clear. It's not a trivial problem. So give me a suggestion or 2 or 3, and we'll see what might be whether they meet these goals, and we can try to fix those problems. Yep.
First node gets to go first.
First node gets to go first. Presumably, there's a second node that gets to go second, and so on.
It's, I guess, it's like when 2 cars arrive at a stop sign, the first one goes. Like there's a protocol for.
Yeah, but there you have a visual channel, right? So let's say you and I want to talk. Okay, we both want to talk or express our opinions in this blind Senate problem. We don't have a visual channel. We're blind. Our eyes are closed. How do we decide who gets to speak first? Anurag,
If
yeah.
I want to speak and no one else is speaking, then I can start speaking.
Okay, so it's a very simple protocol, incomplete protocol, I'd say, to the extent Anurag had time to explain it. He said, if I want to speak, I'll just stop speaking. That's the protocol. Alright? This is actually not bad. Ethernet, to some extent, or in part, does this. If right now there's silence in the room, and you're one of the people who wants to speak, just grab the channel, just start talking. Okay? There is an obvious problem with this. What's the problem with this? Yeah?
If everyone's gonna do that, then everyone's gonna speak at the same time.
It is possible that multiple people start speaking at the same time. Okay? Let's say I start speaking right now. Okay? So I want to say, I think gun rights should. I'm not even going to try to end that sentence, right? So that's enough. I started saying, I think gun rights should. And before I even completed, I think, somebody else, also Joe started with, no, I think, right? Because why can this happen? Two people can start simultaneously. Well, it's not just that two people can start simultaneously. Of course it can happen then, right? If both of us started at the exact same femtosecond, that can happen. But we don't need to be so much synchronized. When I start saying, I think, that's sound. Sound travels at some 330 meters per second. It takes some time for my sound waves to reach Joe. And by the time my sound waves have reached Joe, he has started speaking already himself also. So whatever you guys are hearing, you might hear my first word, like I, or I think, clearly, because there was no collision then. But if you think of the whole sentence as one packet, my packet and Joe's packet overlapped like this when they arrived at your ears. That's garbage. If two packets collide, their bits essentially get scrambled in the channel. That's the problem that's occurring. So the delay really matters. Okay? The longer the delay, the harder this problem becomes. This is also a problem that can happen with just two people. It doesn't need a room, right? You've all seen the scenario of like long distance phone calls, satellite TV-based newscasters, where you've seen this problem of a lag, where you can see that the person at the remote end in some war zone or something, you can hear, you've already heard the question, but the person on the remote end just looks dumb, right? So I found a funny video on YouTube for this. I hope my browser window is still open for that. Okay, there we go. I don't know if the volume will work. Hopefully it does.
Yes. Ski tours the highest food travel trend, ecotourism.
I know, I'm excited. I think we've got Denise now. Let's go to her live in the rainforest of Costa Rica. Hi, Denise. Good to see you.
Thank you, Tom. Hi, Megan.
Looks like the climate
How long have you been down there? Yeah, I think there's a delay. Thank you, Tom. Denise, we're gonna say goodbye to you for now, I think.
Oh my God. Do you see that? Denise! You have a huge spider on your shoulder.
What?
Well, alright, so I'll stop right there. Few takeaways from this. First, there's an exaggeration, right? Second, I'm trying to speak up. problem is realistic. If you were trying to just talk with two people, this is essentially two people, two parties on either side, this kind of interference can still happen. Because one person can start saying, start a sentence, collide with the other person, because before the sentence has reached the other end, the other person has started speaking. And then both of you awkwardly might, in this case, that's not happening, both of you might awkwardly pause and say, you go ahead first. And that might collide again. Both of you might simultaneously say, you go ahead first, or like sort of more or less simultaneously, and then you might pause again. And you, as humans, even if there's long delays, we somehow kind of figure out that there's long delays and adjust our communication to be able to make progress. This is with two people. With more than two people, it's going to be even more of a problem. Okay? This example, the delay part is right, that these delays can make communication uncomfortable, and it can take some time to get used to it. But the spider part is just S&L, right? That part cannot happen for a couple of reasons. The second reason being that the woman will obviously know if there's a big spider on her. What's the first reason? What's the technical reason? Yeah?
I assume she is someone filmmaker or
No, that's still a low-tech reason. Yeah. Well, correct, but whatever the audio and video in this case, actually there's not a different visual channel. The audio and video in this case is exactly the same channel. Okay, so if there's a spider right now and its video is coming to you, then you're seeing what's happening, just a fraction of a second before. So it's sort of not possible that the audio of something gets to you, the video of something doesn't get to you in a video conference like this. That part doesn't really make sense, but all the rest of the delay in the communication, causing collisions or causing these lags. This is the problem that multiple access needs to do with. Okay? So, how else can we solve this problem? Yeah?
You just wait a random amount of time.
Wait a random amount of time. That's actually very good. Okay. Which is how we end up solving this communication problem in phone calls, right? If you find that we're colliding, even as we're trying to give way to the other person by saying, okay, you go ahead first, and we find that we both collided again, then we just kind of back off and slowly figure out like how much to back off. And essentially, at the end of the day, it's random. One person decides to then go ahead because there's silence for some time, right? This is called a random access protocol, but there's a few other very simple techniques that should be fairly familiar to you that are called, the first of which is channel partitioning. Random access is what I just talked about, and then there's another class of protocols called turn-taking protocols. So channel partitioning is like TDM or FDM, frequency division multiplexing or time division multiplexing. We've seen these kinds of protocols in a different context, in a resource allocation context before. In channel partitioning, let's say, I speak for the first 5 seconds. Tom speaks for the next 5 seconds. Carlos speaks for the 5 seconds after that, and so on. That's just we're dividing time. Yeah?
So would this be pretty similar to like a round robin, basically?
Yeah, essentially a round robin like protocol. But it has a problem. It doesn't satisfy one of these problems. Those we want. So it's not a good protocol. TDM or round robin. Well, let's actually, there's a slight distinction between TDM and round robin, I'll come to that, but let's focus on TDM. First slot is mine, slots are of fixed length, first slot is mine, second slot is Thomas's, third slot is GC's, and so on. In this TDM protocol, it doesn't satisfy one of these 4 goals. Which one of these 4 goals does it not satisfy? Yeah.
Yeah, it requires some sort of synchronized clause or something.
Yeah, but it doesn't satisfy one of the first 2. The first requirement says when exactly one node wants to talk, it should be able to use all of the channels. Let's say I'm the only one that wants to talk. I'm going to be, if there's 90 of us right now, I'm only getting 1/90th of the channel. I speak for the first 5 seconds slot, and then I have to wait for 90 times 5 seconds before it's my slot again. But if there's only one speaker, they should be able to use the whole channel. So that's a proper, that first goal is not satisfied by channel partitioning schemes. FDM is very similar to TDM, it's just a different way of cutting up the channel. Instead of time, you're cutting up in terms of frequencies, right? You've allocated, it's just like circuit switching is inefficient because it's like having a lane for yourself, but then if you're not using it, it goes idle. So channel partitioning schemes have this problem. Turn taking is somewhat similar in spirit, it's subtly different from channel partitioning schemes. Turn taking could be like a token ring protocol, right? So I have, let's say I have this pointer, a slide pointer. This is our token. Whoever is holding the slide pointer is the one that can speak. This works for the blind center problem, assuming that we have a way to pass tokens. If I want to speak, I will speak right now. When I'm done speaking, whenever I'm done speaking, I'm going to just pass this token over to my neighbor. And we have an order. It's called a token ring because it's a ring order along which the token gets passed. So this ensures no collisions can happen because there's at most one node that can speak at any point, the one that's holding the token, and we have a fixed order of token passing. What's the problem with this? Well, what about the first problem that we said with the previous one? If only one node wants to speak, it should be able to speak using all the channel. If I'm the only one who wants to speak, I can keep holding this token and keep talking for as long as I want. Okay? But then if 4 of us want to speak, I need to release this token at some point in order to get it to one of those 4. What am I going to do? So we might come up with a fairness scheme saying, okay, you can talk, but you can only talk for 10 minutes at a stretch. So after 10 minutes, I'm going to give it to Thomas. Thomas is going to take 1 second, or maybe 2 seconds to decide, oh, I have nothing to say. And he's going to pass it over to Carlos. Carlos might have nothing to say. He might take a second or 2 and decide to give it to his neighbor and so on, until it gets to, say, Anurag back there, who has a 10-minute speech to give. So we're wasting time passing the token until it gets to one of the nodes that wants to speak. And once they have spoken, the token has to go all around the ring and then come back to me, even though there might be nobody else who wants to speak. So it has inefficiencies. And if for some reason, say Joe is holding the token right now and he just faints, then we have a problem. That's it. Nobody can speak at this point. It's not fault tolerant either. So back in the 70s and so on, people tried a variety of schemes like this. Multiple access schemes, and Ethernet sort of won the day. And Ethernet is still the most popular link laying protocol we use today, and it's based on random access. Random access is most intuitive to how human beings also resolve these kinds of human beings on a phone call, or equivalently in this blind Senate problem scenario, end up resolving these kinds of conflicts, essentially using randomization. So to understand how Ethernet does this, we're going to see an even simpler protocol from 70s. This is a real protocol, a protocol. I've covered this. Okay. So a protocol called Aloha, right? Or specifically one called slotted Aloha, and then we'll see the unslotted version. This is based on randomization. It's a very simple protocol. It's widely considered as a precursor of Ethernet. Ethernet is fundamentally based on this idea, but it's some of the design implementation details are different. It's called Aloha because Noam Abramson, who's the person who invented this protocol, he went to the University of Hawaii because he was into sailing a lot, right? He just happened to do this as part of his PhD work. What is the protocol? The protocol is very, very, very simple. That's why we're looking at it before we look at Ethernet. Time is divided into slots. Okay. For now, dividing time into slots requires synchronized clocks. So before you ask me, well, it's not simple, it requires synchronized clocks, we will remove the synchronization requirement in a second. First, assume that time is divided into synchronized a node can only start speaking or transmitting at the beginning of a slot. So let's say 1 second slots. You can start speaking at the beginning of second 3 and go into the end of second 3, right? The 4th second is a different slot. Nodes' clocks are synchronized. If 2 nodes speak in the same slot, there's a collision. No, that slot is wasted. Nobody can hear anything in that slot. Any transmission, anything that was transmitted in the slot. Our operation is dead simple, okay? Whenever a node wants to speak or transmit a frame, size of the frame assumed is the length of a slot, or the size of a frame is equal to the transmission delay that corresponds to the length of the slot. If it's small frames, you can assume frames are padded, right? We'll ignore the difference in frame sizes and slot sizes. If there's no collision, we'll also assume that there's some way to detect a collision, which is true in practice. When a node sends a frame, it can also hear the frame itself send and see if it can decode the frame correctly. If it was able to decode it correctly, everybody else will also be able to decode it correctly. So there was no collision. So if there was no collision, I just sent a frame in slot 3, then I'm going to go to the next slot and also continue transmitting in slot 4, slot 5, slot 6, and so on. So if I'm the only person speaking, I will have a full channel. Any slot, there is a collision, assume that we can detect it, remember? So if I detect a collision, then in the subsequent slot, I will probabilistically transmit, I'll back off, which means even if I have data, I'm not going to necessarily transmit it in slot, I'm going to transmit the probability. P is a parameter of this protocol. Theoretically, here's how it's, and that's the essence of randomization in this protocol. Theoretically, this is how it's working. In the first slot here, it shows you nodes 1, 2, and 3 all wanted to speak. There was obviously a collision. They all detected that collision. In the second slot, because they just detected a collision, they're all going to toss this coin, which is going to come heads with probability P. Heads means you can talk. They tossed the coin in slot 2, nobody got a heads. So nobody spoke anything. So in the first slot, there was a collision, that's C. Second slot is just empty. Third slot, the probability turned out so that both 1 and 2 got a heads. There was again a collision. In the fourth slot, they both detected this collision and again probabilistically tried the 1, 2, 3, 4th slot when node 2 happened to finally succeed. So in the fourth slot is when, with the probabilistic P, it allowed exactly 1 node to transmit. Again, 5th slot is empty, 6th slot is a collision, 7th slot is empty, 8th slot is when node 1 finally got its transmission, and the 9th slot is when node 3 got its transmission. Successful transmission. Anything where there's more than 1 frame that's marked with a C, that's a collision, nothing got through. Anything where nothing is sent, nothing got through. So the pros of this scheme are it's a really simple scheme, but the cons are some slots are going to be wasted, like shown. Startup next class, we're going to do the computation for how efficient in a protocol